So in the application, when we have these nodes or these vertices, um, and we have you know, we have like Boston, and then we have like New York, and then we also have, let's say, um, Washington, and we have a network. Let's go a very simple network that connects all three. Um, Now, these nodes right now are these vertices. We have B, N, and W. So our vertices here we can say are B, N, and W, with our edges, of course, being, and this one being an undirected. It could be directed, but there's both directed and undirected. You'll see both in your homework tonight. We have a BN, we have BW, and we have NW. So just like a normal network, we have these connections. But what we can also have is what we refer to as the weight. We can give each of these a weight or a cost, and these costs can represent various things. We can add weights. These represent cost, which could be time. It could be actual money. Or it could be, it could be really anything else. That's how many times you have to do something, or how many times along the way something occurs. And for the simplicity's sake, we'll talk about time. So we can put like a 4 right out here. We can put an 8 right here, and we can put like a 5 right there. Now, these are weights. These weights can represent, for example, we're not going to get into giving these actual weights any explicit application today. Right now, they are just values that are on here, and we're just going to try to represent what they are as such. But in this case, they represent how many hours it takes. Typical hours to get from Boston to New York, about 4 hours. Boston to Washington, about 8 hours, maybe 9. But just when I'm trying to be like really, really precise here. And New York to Washington is 5. And if you want to go from New York to Washington to Boston, we call that a path. We're going to talk about that tomorrow, paths. We can take various paths, so we can go from New York to Washington to Boston, which is a very long path, and B, New York to Boston, we do have a direct path from New York to Boston, and it would seem better to go that way. But that's not always the case. It's sometimes true, as you think about like airlines. Sometimes it's not the cheapest to go from one vertice to another vertice, from one city to another city. Sometimes it's actually cheaper to go just do a layover, stop here, and then go over. If we were talking about the cost of money, but then if you probably adds more time than a direct. But that's how we have to do it. And then sometimes there is no direct path. In this instance, there is. But if I were to add in another one, Philadelphia, for example. Let me change the color actually. Maybe Philadelphia only connects to New York. So to get to Philadelphia, you have to go through New York. There is no direct from Washington or Boston. Or actually, I can do it like this. No, right here. So now, if we're starting at Washington, we have no direct path to get to Philadelphia. You can't just go directly to Philadelphia. Um, so you might have to um, add in. You have to go to New York and then Philadelphia, or you have to go from Washington to Boston and then Philadelphia. In this kind of example, so we will be talking about that. And we'll put a little bit more focus on that tomorrow about why these, what are these things called paths. But right now we just have these weights that are attached to them. Okay. So how do you represent them? All right, and that's kind of like our focus today. How do you representing? So representing weighted graphs. The answer is just a matrix where instead of 1, we use the weight of the edge. So instead of using just a bunch of 1s everywhere, we're going to actually put in the actual weight of that one. So let's do an example. Let's do the example above. Let's represent the above, including Philadelphia, the above weighted network as a matrix. And there's a lot of application once you go here. And there's a lot of stuff in regards to the computer science world, in regards to, just overall in applications. This is what Google Maps does for you, basically. Um, it's the problem here, and as people are writing down this and catching up, right here, right now, there's only 4 different. There's 1, 2, 3, 4, 5. There's a total of 5 edges. 5 edges doesn't sound like that much, and we can actually see and look at every single possibility. All right, that's not that much of a problem if we only have these 5. We can what we call number crunch. If I wanted to get from Washington to Philadelphia, we could actually look at every single possibility. All right, an idea that we're going to do tomorrow. We can go from Washington to Boston to Philadelphia. We can go to Washington to New York to Philadelphia. We can go from Washington to Boston to New York to Philadelphia. Who would want to do that? And we can go from Washington to New York to Boston and then to Philadelphia. It doesn't seem like it's the smartest thing. Like, why would you want to do that way? But sometimes maybe, there's an accident. And there's the travel is down in one neighborhood or whatnot, so the cost becomes really bad. That if you want to go direct from Washington to New York, maybe that does no longer become an option, or maybe the cost really blows up right there. And same thing happens in Philadelphia. So maybe you have to go to Boston. You have to zigzag your way through. It happens. Once you start adding more and more, once you start adding more places that you can go, and if they all connect, mathematically the answer comes up into the millions and then billions and then trillions of possibilities very, very fast. and I'll reference this tomorrow. There's a famous application called the Traveling Salesman. All right. Um, let's say we want to get to every city, so we start in Washington and we want to make sure that we get to every city, and we want to do it at the lowest cost possible. What is the path I should take? Should I go to Boston first? Should I go to New York first? Okay. And in something that's very low, there's only these 4 locations. It's not that bad. But when you add in like 10 cities, even once you get to like 10 cities, it becomes um, far too many possibilities. And basically what we do is we utilize computers and we use things called algorithms um, to find the best possible method. But in the reality, there is no true solution. Sometimes it's a very famous problem because there is no way to just systematically do it. And I'm gonna talk about that tomorrow. Um, kind of like what we can do, kind of just see the applications. But it's pretty cool stuff. So how am I gonna make a net? How do I make the matrix? So what do I do with this matrix? Can somebody just briefly explain?
You do the box with you add 1, 2, 3, 4 lines. Then you write 4, 5, 8, 9.
No.
Oh no? Oh. Oh no, Boston, Washington, New York, and Philadelphia.
So we labeled the vertices, and we could just use their first letter in this case right here. In your homework, I do not have them as actual names. They're 0, 1, 2, 3, 4, or they are A, B, C, D, E. In this case, we could also say Boston is 1, Washington is 2. We could have made like a key like that, and then did 0, 1, 2, 3, 4, 5, and so forth. Now, what do I do next?
The zeros.
Yeah, and they're all zeros because there's no internal loops of going back on each other. In our course, we're not doing anything like this. All right, so we're not going to do any of those. So zeros always go along our diagonals. Good.
You have a 1 in Boston and Washington.
Mm-mm.
BW.
No.
You don't.
Remember, this is new. Anybody, what do I put there? Right there. Instead of a 1.
Use the weight of the edge. So you put A.
There we go. And the next one over?
Boston. Be 0.
Boston to New York?
4 to 4.
And Boston to Philadelphia?
7.
Good. Washington to Boston?
8.
And in this example, we can go in both directions. So inside your homework, like I said, you have some ones that are only one direction. You can only go from one place to another. You can't go backwards. So that'll happen. Washington to New York.
5.
And Washington to Philadelphia.
Where's Washington? Oh, you add 8 and 7, or is 0?
It is 0.
0.
There is no direct. You can. There's not an edge from Washington to Philadelphia. New York to Boston.
That will be 4.
New York to Washington.
5.
And New York to Philadelphia.
9.
Philadelphia to Boston.
7.
Philadelphia to Washington.
0.
And Philadelphia to New York.
9.
So the material is just the same. That if we have any just one direction, you can in this case you can go from Boston to Washington and Washington to Boston, just like you did in your homework problems last night. Sometimes you would only have only one of them. You can only go from Boston to Washington, but you can't go backwards. That might occur in some of your homework problems tonight. It is a synchronous, asynchronous day. As such, I don't want to keep you entirely for the class. I've given you pretty much the background information that I wanted to give you, as well as one of the examples. I think you should feel comfortable after Eliana helping us walk through this weighted graph in here. Tomorrow we talk about paths. We're going to talk about adding them. Like Eliana was saying, like, oh, if I want to go from Washington to Philadelphia, he was like, I can add the numbers. We're going to talk about that part, and that's what we're going to be on tomorrow during our synchronous lecture. I'm looking to close it out on Friday with graph theory so that next week we can just do a quick kind of assessment on it using Monday and Tuesday as our assessment days, and then call it a close for Christmas break so that there's no extra work. So just to kind of give you a preview of what I've been thinking about and planning for us for this unit. With that, the remainder of class is asynchronous. Remember, this class ends at technically 8:55, which is 22 minutes, with our next class starting at 59. So 50-minute classes plus 4 minutes passing periods. It is Wednesday, bell schedule. Don't forget CAS is after your B block. With that, if you don't have any questions, have a good day. If you do possibly want to do the homework and have questions, I'll put you into a breakout room so you can hit that help button. Take care, everybody.